Fields.
Thanks. So to start out, let me remind you where we ended up last time. Which we're going to start with a, thank you. A Gorenstein normal domain. Not necessarily local, say. Then I can never decide. Okay, NCCR. This appears to be the accepted thing now. We're going to just call them NCCRs. A non-commutative Crepant resolution of R. Of R is an R algebra. Say lambda, which is an endomorphism ring of some finitely generated, all my modules are finitely generated, so that's, I will stop saying that, reflexive R module M, such that it has finite global dimension, lambda does, and lambda is maximal Cohen-Macaulay as an R module. Equivalently, lambda is a birational symmetric non-singular R order, which takes up fewer lines. I guess it doesn't really do anything in this order, but you could reorder so that it was not. I don't know. And one of the points was that the fact that this is equivalent relies heavily on the assumption that R be Gorenstein. So here's the first question. What is a, or maybe there's a unique, correct definition for R not necessarily Gorenstein? And it's sort of kind of a cheap question. I'll give you an answer. There is an answer. But I kind of think that maybe there should be others. So here's an answer due to first Iama and Weems in the Cohen-Macaulay case, and Dow, Faber, and Ingalls more generally. So let's suppose that R is just a normal domain. You don't even really need this, but let's go ahead and assume this. Then a NCCR of R is, again, an endomorphism ring for M just a torsion-free R module, which is a non-singular order. It's not completely clear to me that this is the unique best definition, though they do have some very good results with this. Okay, so that's all mostly recap from last time. And what I want to do today is to describe two sources of these things, both of which have actually already come up in lectures yesterday or the 5-minute lectures on Monday, but I want to take a slightly different point of view on them that perhaps will be illustrative. So, the first is quotient singularities, which was already very well discussed in Spilespenko's talk, but I want to describe only the finite group case, and I want to highlight a couple of different aspects. So, what is the setup? Let's take a field. I don't care whether it's algebraically closed. Let's take G a finite subgroup of GLN over that field, and let's assume we're not in any sort of bad modular situation. Take S to be the polynomial ring over that field in n variables, with G acting linearly. In the obvious way. And let's set R to be the ring of invariance. So, for example, and this is a good one to keep in mind as I go through, just take two variables, and let's take, I better not use n, I better use m, say. Take the M Veronese subring of polynomials in two variables. Keeping this question in the backs of our minds, I want to point out here that if I call this R is Gorenstein if and only if M is 2. In general, and this is going to become central, in general, if your group G is contained in SLNK, then the ring is Gorenstein. And the converse is mostly true converse is true if we assume that G is what's called small, which again came up in Spella's talk, which means that no non-identity element fixes a hyperplane. Yes? Good. Okay. So we always have, in this situation, that R is a Cohen-Macaulay normal domain. either by the Hochster-Roberts theorem if you want to use a big gun, or direct computation of the Reynolds operator. And more importantly for my purposes, S is a maximal Cohen-Macaulay R module, which I've been throwing this MCM around. Maybe this is a good time to give you one definition if you've just been sort of nodding along up to this point, pretending that you got it. One way to say that S is a maximal Cohen-Macaulay R module is to say that S is free over a polynomial subring finitely generated free over a polynomial subring of R. So, for example, in this example back here, you could take the polynomial subring in x to the m and y to the m, over which the full polynomial ring is a free module. Good. Yeah, I'm just not going to bother. Now, in this situation, we define something that, again, has come up in a talk or two, the twisted group ring, though I don't think it was ever formally defined, so I'll go ahead and tell you what it is. S hash G. Didn't used to be called S hash G. It was only with the advent of Twitter that I started calling it this. I don't know if you know this, but so Toby had this great line in his lecture on Monday about updated BAS, the ubiquity of definitions of Gorenstein rings. So this is the world we live in now. I tweeted this because that's who I am and that's the world we live in. And got an immediate response. So, live blogging Stafford's lecture? There are people watching. As it happens. Backs of your heads. Look, I may not be able to continue. Okay, here we go. Here we go. The twisted group ring is the free S module on all the elements of G with multiplication twisted. So elements look like, say, S sigma, and another one might be T tau, and you multiply them by, since you have to scoot the sigma past the tau, it twists tau by this automorphism sigma. And it's a known fact that modules over this twisted group ring is equivalent to G equivariant S modules. In particular, this means that the global dimension of this twisted group algebra is finite, actually equal to n. Now, that twisted group ring has a natural homomorphism ring homomorphism, let's call it gamma, say, to the endomorphism ring of S as R module. And it is sort of the silliest homomorphism there is. Things over here are endomorphisms of S. They're automorphisms of S times ring elements. So you just view them as endomorphisms, and they happen to fix R because R is the fixed ring. And the theorem, which is due to Auslander, is that if G is small, this condition on the middle board, then gamma is an isomorphism. So putting together the piece on the far board and the piece on this board, we see that the endomorphism ring over our quotient singularity ring, the endomorphism ring of the polynomial ring, is a maximal Cohen-Macaulay R module. It's a free S module, and S is maximal Cohen-Macaulay, so it's still maximal Cohen-Macaulay R module, and has finite global dimension. So if R is Gorenstein, it is one of these non-commutative Krepin resolutions, which we've only, I'm going to stick to this, only having defined it in the Gorenstein case, even though it also would work for this definition. Let me say just a couple more words about this example, but let's talk about the case n equals 2. That's where everything good happens. Oops, I'm supposed to, this is the middle board. This is the one that can actually go up. Might as well. In this case, so we're talking about two-dimensional normal domain, R is. In this case, this maximal Cohen-Macaulay condition, which I've made a little mysterious, just means reflexive. It's a much more tractable, hands-on sort of condition. And there are two things that make the case when n equals 2 special. One is a theorem of Herzog from 78 that I shouldn't have to put n equals 2 there, but I'll just reiterate. If n is 2, then every indecomposable reflexive R module is a direct summand of S. In other words, S is a representation generator for the Cohen-Macaulay modules over R. This is utterly, wildly false in higher dimensions. And the second thing, this is Kapranov and Vassereau in 2000. Let's now assume not just n equals 2, but that we are in the Gorenstein case, and that our base field has suddenly become the complex numbers. And let's let Z, Canada, be the unique minimal resolution of singularities of spec R. This is a thing that only makes sense in dimension 2, that there is a unique resolution of singularities once you impose a minimality condition. Then, we have an equivalence of the derived categories between the bounded derived category of coherent sheaves on this resolution, Z, and bless you. This thing, the coherent sheaves on C2 with a little decorated G there, this G means we only look at the G equivariant coherent sheaves on C2. Wait a minute, G equivariant coherent sheaves on C2. That sounds very similar to G equivariant modules over some polynomial ring. In fact, it is. This is mod G of S, say, where again G indicates the equivariance. And this, I'm starting to identify these things, this is nothing but modules over this twisted group algebra. Which is the derived category of modules over the endomorphism ring. In other words, this unique minimal resolution of singularities, if you are wearing your derived blinders, is indistinguishable from this non-commutative ring. In some sense, this endomorphism ring is a, or maybe even the, preferred resolution of singularities. What about n equals 3? I already said that this one fails. Herzog's theorem fails. Kapranov and Vassereau's theorem continues to hold in a certain slightly revised sense. This is a theorem of Bridgeland, King, and Reed from, I think, 2001-ish. So again, let's assume we're in the Gorenstein situation. We're working over the complex numbers. Then there is a resolution of singularities, Z, such that you again get a derived equivalence. which again, by the same string of equalities over there, is nothing but modules over this endomorphism ring. I guess there's no particular reason to be cagey about what this Z is. It's the same thing that it was over here. It's a certain G equivariant Hilbert scheme, to make a connection with Toby's talk. And as a last observation before I finish this example, oops, up there. Let's call it a remark. These, by which I mean the two theorems of Kapranov, Vassereau, and Bridgeland, King, and Reed, are both false if the group is not contained in the special linear group. But, once again, Michael Weems to the rescue. With what he calls reconstruction algebras. Which I'm not going to say anything more about. Okay, so that is an abundant source of non-commutative preferent resolutions. Let me now switch gears and do something quite a bit different. So we'll call this example 2. Tilting as a source of non-commutative preferent resolutions. So let's consider a tilting bundle, and I'll only ever talk about tilting bundles today. T on a, let's say, a scheme X, by which I mean two things that T generates the perfect complexes over X and has no self-extensions. Let me say it like this. Hom in the derived category between T and all the shifts of T. These are all 0 if I is not 0. Oh, I did it, didn't I? Okay. The point of this definition is to write down the following theorem, which perhaps you might call the fundamental theorem of geometric tilting. This version comes from a survey article of Lutz Hille and Michel Vandenberg. There are other modifications, but this is the one I want. So let's let X, take a scheme X, call it Y, be a scheme, let's say, projective over an affine base. And let's let T be a tilting bundle. And let's let lambda be its endomorphism ring. Then the functor Arham T blank, which eats coherent sheaves on X and spits out modules over the endomorphism ring, is an equivalence. In particular, X is smooth if and only if lambda has finite global dimension. At which our ears perk up, yes? Endomorphism algebras of finite global dimension are of particular interest to us. So this suggests a strategy for producing endomorphism rings of finite global dimension. And if we're particularly lucky, producing non-commutative prevalent resolutions. So let's start with some singular thing. Oh, I know why it was supposed to be called Y. Because it's Y in this board. Oh well, you'll have to cope. Some singular thing X, which is sec of a ring R. Resolve its singularities. Say, on Monday I used this notation pi from x twiddle to x, and construct or obtain or beg, borrow, steal a tilting bundle T on this smooth thing upstairs. Then in good situations, this endomorphism algebra of T will be an R algebra. It will have finite global dimension. And possibly other good properties if we're exceptionally fortunate. So we have only really, what could this ... be that would be interesting to us? We would like to know that it's maximal Cohen-Macaulay as an R module. And in this situation, there's a theorem that tells you when it is. So this is another theorem of Osamu Iiyama and Michael Weems in, I think, 2011. To be honest, there are so many I have trouble keeping track. Let R be a Gorenstein normal domain. So we're back now in the Gorenstein situation. and let f from y to x I'll make sure I get all the hypotheses correct. Projective birational map with y also Gorenstein, a Gorenstein variety, normal as well. Maybe it's worth spelling out here. The example we're thinking of is, of course, that y is a resolution of singularities of x. Let's take a tilting bundle on y, and as always, lambda its endomorphism ring then the following two statements are equivalent, and I'll sneak them in here. This ring, lambda, is Cohen-Macaulay, maximal Cohen-Macaulay as an R module if and only if pi is crepant.
Pi is F?
F, of course, thank you, yes. F is crepant, which now, I think I managed not to write it on the board yet today, but of course I wrote it on Monday and didn't explain it, so let me take a couple seconds just to say what it is, and then I'll say more on Friday. i.e. that F upper star of the canonical bundle on X is the canonical bundle upstairs on Y. So this is, I think, a very strong validation of Vandenberg's choice of terminology, that such a thing, an endomorphism ring which has finite global dimension and is Cohen-Macaulay as an R module, deserves to be called a non-commutative crepant resolution. I do want to put here a warning. Since we've already talked a little bit about the question of correct definitions in the non-Gorenstein situation, and we see a Gorenstein hypothesis there on the board, what happens if R is not Gorenstein? It can still happen that you get a maximal Cohen-Macaulay module even if F is not crepant. In that case, of course, you can't use this theorem, but you can one typically has to work with an explicit tilting bundle and actually get your hands dirty and prove that it's Cohen-Macaulay directly. So to finish, let me, one more thing. I had one more thing I wanted to say about this. And maybe I won't write it, I'll just say it. This is good news. This is not something to cry about. This is good news because in dimensions 4 and more, remember we had good situations when n was 2 and 3 in the Mackay correspondence. When n is 4 or more, there are hardly any crepant morphisms. So you wouldn't want to have to assume that F was crepant to get a Cohen-Macaulay module. We're hoping to get by with much, much less. So this is a hint that if the ring is not Gorenstein, the terminology needs to change somewhat to not evoke this crepant condition, which is just too strong, probably. But anyway, as I say, let me give you a quick run-through of one situation where this all applies. Which again appeared in Spela's talk. Let's talk about determinantal varieties. So let's let R be a polynomial ring in some variables xij modulo the t by t minors of the matrix xij, where xij is some m by n matrix of indeterminates, and we are killing the t by t minors so that we get my indexing going to be off? My indexing is always off by 1. No, good. So this is the space of m by n matrices of rank less than t. This thing has an explicit resolution of singularities, which again I'll call Z, but I won't explicitly tell you what it is. It's easy to look up, has a Wikipedia page and everything. And because I'm acutely conscious that I'm the only thing between you and your free afternoon, I'm simply going to say that together with Ragnar Buchweitz and Michel Vandenberg, we were able to prove that there is and for an extra added degree of difficulty, like gymnastics, it's characteristic free tilting bundle. Let's call it T again for continuity, on Z such that the endomorphism ring is a, I'll be a little fast and loose here, has finite global dimension, and is maximal Cohen-Macaulay. As R module. This map from Z to X is only crescent if m is n, that's the only time when this ring is Gorenstein. So in all other cases, you have to roll up your sleeves and work for a living. Speaking of which, happy afternoon vacation. Thanks for listening.
Other questions?
They're already gone. They're already gone.
Let's take